In this question, they're giving us a function and they're telling us, hey, here's the function, prove that this, or show that this function has no stationary points. So it's a bit tricky because most of the things we've done till now, they've actually said, hey, it has a stationary point, and then we find the derivative and we say, okay, dy dx is then going to be equal to 0, and then we find some values, and that's perfect. But in this case, there's no stationary point. So where a lot of the curves that we've dealt with, I mean, this is as a cubic function, would have looked like this, and we would have said, okay, well, here's a stationary point, and there's a stationary point, and we would say dy over dx would then be 0, and then we'd solve some kind of a thing, and it'll give us some x values, and then I'll be like, okay, the x value for that stationary point, and the x value for the stationary point is this, etc. But now there are no stationary points, so this curve kind of looks like this. So it kind of has this bending and the little kink, but they're not actually stationary points. So it's an increasing function, but there are no stationary points, and they want us to prove this. Now, before we can go to that, I just want to draw let's say a normal cubic function that we're used to. Let's say we had something like this. And let's just draw our axis, and then let's make it, let's say, something like this and like this. And this is my x and my y axis. And here is just some random, it's obviously not this one, but this is some random cubic function. So if I were to look at this, then that would be a stationary point, and this would be a stationary point. Obviously, it'll be more symmetrical. But if I then had to derive this function, the blue function, and I drew its, let's say, the gradient function or the derivative, if I graphed that, what I would see is that I'd actually obviously know this is a cubic function is to the third degree, which means the highest power is a 3. And once we derive, we see that it, like a cubic function derived, would become a quadratic function. So we'd have this, and then obviously when we derive that, we'll get a parabola because that's a quadratic function. If I had a parabola or a quadratic function, I'd derive it, then I'd get a linear function. So this is kind of what happens when deriving. The degree of the function is getting less. Now, if I derived this point right over here is a critical point, because that is where this, let's say this function has a stationary point, and also this on the x-axis would be a critical point. And what we would see is if I were to derive this function and I drew that function, the derivative function, it would actually form, I'm going to do it in red, it's going to form a parabola, and it'll, I hope that's okay. It'll actually intercept the x-axis at these two places. It'll be exactly aligned with the stationary point there and the stationary point there. Because where the derivative, this is, okay, let me just write this. So if this was my normal function, f of x, then this would be my derived function. And I would see that the derived function actually intersect the x-axis at exactly these two places. But what do I know about parabolas? Way back when we did some, maybe, well, you should know what the discriminant is. So the discriminant is that part in the quadratic formula that's b squared minus 4ac. So that's the part that's underneath the square root, if you remember that. And we kind of usually use that for to figure out whether let's say a parabola intercepted the x-axis or not, so whether a function would have roots or not. And we saw that if the discriminant is bigger than 0, then we'd have two roots that would work, or basically there would be, it would intercept the x-axis at 2 points. If the discriminant was equal to 0, then we'd have one root. We'd have kind of this like, let's say that would happen for the two roots. If I had one root, it'll just touch. And then I also saw that the discriminant, if it was less than 0, smaller than 0, there wouldn't be no roots. And that's a case where it never intersects the x-axis. So what's going to happen in this case, if this function, or let's say if this function had no stationary points, if I drew the derived function, it would not cut the x-intercept. So basically, for a function like this, where there's no, okay, well, that looks like a stationary point, but just ignore it. Then what would happen is, if I were to draw the derived function, it would not actually cut the x-axis. It'll just be somewhere in the air above there. And the way I can now use this information is I can actually take this function, I can derive it because that's the gradient function, and then that derived version I can check what the discriminant is, and because it has no roots, I'll know there will be obviously the discriminant must be less than 0. And well, we'll take a look at what happens further. In this question, they're saying show that. Well, they didn't say, yeah, show that no stationary points. And then the other part of this is, maybe I should just write that down. They asked us to show that a squared is smaller than 6b. So this is kind of what we need to show. But I know that was a very long explanation of just saying if a function has no roots, then the derivative function will not cross the x-axis, and it will have no x-intercepts, which means that if I were to look at the derivative, sorry, not the derivative, the discriminant, it would have no roots. So let's see where it takes us. Hopefully, all that talking means something to us. So let's take a look at what's going on. Okay, so I'm gonna first derive this, because I need to figure out, obviously I need to find out what the gradient function is, or the derivative. And if I were to derive this, that would be 6x squared plus 2ax plus b, and the rest would just disappear. And knowing this is a parabola, and because I know this has no roots, I know the discriminant of this would be less than 0. It would be smaller than 0. So if I were to do, let's check a different color. Let's do b squared, plus 4ac. This should all be smaller than 0, because then I know there will be no roots. So let's hope for the best. Let's see what happens. I'm just going to write here on the side obviously this is A is 6 and B is, in this case, it's 2A, and C is B. Okay, that's not confusing at all. Okay, so for B, it's B squared, so 2A squared plus 4A, that's the 6, and the C, which is the B. This all should be smaller than 0. If I square all this, I get 4a squared. 4 times 6, I think that's 24, and the B is just there. And now I kind of have to, if I look at this and I look at this, I'm like, it looks very similar. I'm almost there. Did I make, oh, there we go. Oh, someone might have caught up. It's minus. I was like, why? Something is a bit off here. Okay, so the discriminant is obviously b squared minus 4ac. Not really sure why I put plus there, but hopefully you'll be able to forgive me. 4a squared, taking this over becomes, well, also, or add 24b on both sides. Then I have 24b on this side. And now I can just divide by 4, and I would have, okay, I can make a better a than that. A squared is going to be, smaller than 6b. And this is exactly what we proved. So the trick here was kind of remembering that the discriminant can be used on my derived functions. And it's not just, hey, this arbitrary thing we learned a long time ago that has no use for us. It's actually very, very valuable in finding out whether functions have has stationary points or not.